Hello. The Chapter 3 practice work that I posted, the majority of this work deals with studies involving electromagnetic radiation and their electromagnetic spectrum, as well as focus on conversion of units. And so, with the first question being one that involves doing unit conversions, in doing these unit conversions, one of the important aspects is knowing what the conversion factor is that you must use to convert between one unit and another unit. And so for the first one, part A of number 1, you are converting 125 centimeters into meters. And so therefore, the conversion factor being that for every 1 meter, you have 100 centimeters. So 1 meter per 100 centimeters. And so therefore 125 centimeters is going to be multiplied by that conversion factor. I want to convert from centimeters to meters. So in my conversion factor, centimeters, the unit I want to convert from or get rid of, will be in the denominator. The unit that I want is meters, so that unit needs to be in the numerator of my conversion factor. So I'll multiply 125 centimeters times my conversion factor. The centimeters cancel. You do the math. 125 times 1 is 125. Divided by 100, you get an answer of 1.25 meters. For part C, you're converting 400 nanometers into centimeters. And so this one will require two different conversion factors. You'll first want to convert the nanometers to meters. For every 1 meter, there are 1 times 10 to the 9th nanometers. And then, of course, you'll convert the meters then to centimeters using this conversion factor. But because this time you're wanting centimeters and not meters, you'll do the reciprocal of this. So for every 100 centimeters, there is 1 meter. So now to do the two-step conversion, I first take the 400 nanometers and multiply it by the conversion factor that will convert the nanometers to meters. So I want meters in my numerator and nanometers in the denominator. The nanometers cancel. And then I'll multiply by the second conversion factor. I want centimeters, so centimeters go into the numerator. And I'm getting rid of meters. Meters go in the denominator. So now the meters cancel. So now I can do the math. 400 times 1 times 100. And then divide by 1 times 10 to the 9th. And you get 4 times 10 to the negative 5th centimeters. Parts E and F require conversion from grams to moles for part E, and then for part F, from moles to grams, which is the opposite type of conversion. And so for each of these parts E and F, you're given what's called the molar mass for the compound in question. The molar mass is basically the number of grams of a substance per 1 mole of that substance. So the molar mass is always in units of grams per mole. So in part E, SO2 has a molar mass of 64.10 grams per mole. Notice the units. You have your grams in the numerator, your moles in the denominator. So therefore, you can always use molar mass as a conversion factor to convert between grams and moles, or between moles and grams. And so therefore, if we know the number of grams of a substance, and we want to convert from grams to moles, and moles are often abbreviated MOL, then what we'll do is divide by the molar mass. If we want to do the opposite, like in part F, we want to take the moles and convert to grams, then we need to go in the opposite direction and therefore multiply by the molar mass. So to convert moles to grams, you multiply by the molar mass. To convert grams to moles, you divide by the molar mass. So in part E, 125 grams of SO2, we'll convert that to moles by dividing the grams by the molar mass, which is 64.10 grams per mole. The grams cancel. And so you take 125, divide by 64.10, and your answer is 1.950 moles. Note that your starting number, 125.0 grams, has 4 significant figures. So therefore, my answer should also have 4 significant figures. For question 2 deals with the concepts of properties of a wave, those properties being wavelength, frequency, and speed of travel. So the wavelength is basically the distance between one peak and another peak. Wavelength is known by the Greek letter lambda, which has this symbol. So that is the Greek letter lambda, which is a symbol for wavelength. So there's the wavelength from the peak of the first wave to the peak of the second wave. That's one way to denote the wavelength, or from the bottom of the trough of one wave, that distance between the trough of one wave and the trough of another wave is also the wavelength. And those are equal. So the wavelength is a distance from peak to peak or from trough to trough. So by it being a distance, wavelength therefore has distance units like meters or centimeters or nanometers. Frequency relates to the number of cycles of a wave that pass through a specific point per unit time. And so therefore for frequency, you'll have the units of cycles per second. Frequency is known by a Greek letter, nu, and that's the symbol for frequency. It looks kind of like an italicized letter V. And so the units for frequency are cycles per second, which are often just called per second. So seconds to the -1 power, which is equivalent to a unit called the hertz. So 1 second to the -1 is equivalent to 1 hertz. And hertz are abbreviated capital H and a lowercase z. So therefore, speed of travel, speed is just symbolized with a lowercase c. And speed, therefore, is going to be equal to the wavelength times the frequency. So therefore, in comparing wave 1 and wave 2, we can therefore say that wave 1 has a longer wavelength, and we can also say wave 1 has a lower frequency. So we can see for wave 1, we only have 2 cycles. But in wave 2, we have 1, 2, 3, 4 wave cycles. So therefore, the frequency of wave 2 is twice that of wave 1. However, the speed of travel of both waves are the same. So again, wave 1 has longer wavelength. Its wavelength is about twice that of wave 2. Much shorter wavelength than wave 1. However, wave 1 has a much lower frequency. However, both will be traveling at the same speed of light. And so question 3 also relates to the electromagnetic spectrum. And we can see here on the figure below that there are 7 major types of electromagnetic radiation types on the electromagnetic spectrum. You have them listed here in order. At the rightmost end, you have your radio waves. And so here you have the longer wavelength. So radio waves have the longest wavelength of all the 7 types of electromagnetic radiation, but have the lowest frequency. So they have the longest wavelength, but the lowest frequency. So you should be able to see by now, in looking at question 2 as well as question 3, that wavelength and frequency are inversely proportional to each other. The longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. On the other end, therefore, you have the gamma rays. They have the shortest wavelength, but the highest frequency. And so in between these two, the next to the longest wavelength are your microwaves. And then you have your IR radiation, your visible light, your UV radiation, and then the second shortest wavelength and the second highest frequency are the X-rays. So here at the top, you have the wavelengths given in meters. So radio waves have wavelengths that range between 1 and 100 meters. Microwaves, their wavelengths are about 1 times 10 to the negative 2 meters. IR, their wavelengths are about 1 times 10 to the negative 5 meters. Visible light is about 1 times 10 to the negative 6 meters. So you can see the wavelengths are getting smaller and smaller as we move from right to left. UV about 1 times 10 to the negative 7, between 1 times 10 to the negative 7 and 1 times 10 to the negative 8 meters. X-rays are even smaller at about 1 times 10 to the negative 10 meters, and then gamma about 1 times 10 to the negative 12 meters. And then what you have here is the visible electromagnetic radiation. And this is just a little cutout of it blown up to show you the different colors of visible light. and their wavelengths in nanometers. And so it follows, and you've probably heard of this in a previous science class, the Roy G. Biv mnemonic. And so your red N, R, those are the longest of the visible light. They have wavelengths of about 700 nanometers. And then the violet end are the shortest wavelength of about 400 nanometers. So red light has a longer wavelength than violet light. Blue comes in at about 450. Green is between 500 and 550. Yellow is about 560, 575, and 600. So between about 560 and 600. Orange is about 650. And then red, of course, is that 700 area, between 675 and 700. And so those are the different wavelengths and nanometers for all the different colors of visible light. And of course, that's the electromagnetic radiation that our eyes can see. And it's referred to visible light, and therefore those different colors of visible light can be separated using an instrument called a prism. And so therefore, using this figure, identify the region of the electromagnetic spectrum where each of the following wavelengths is found. Well, we have the wavelengths in meters. So therefore, whichever wavelength is given in these questions, we need to convert it to meters. So 2 centimeters is therefore going to be, we can convert it to meters. There's 1 meter per 100 centimeters. So we do the math. We get 2 times 10 to the negative 2 meters. And that's going to be in the microwave region. So that's how you do part number 3, question number 3. You take the given units, you convert them to meters, and therefore you find the region that that value in meters is closest to. So for part B, you've got 50 micrometers. You convert the 50 micrometers into meters. Remembering from the previous chapter, your metric system prefixes is very important. So for every 1 meter, you've got 1 times 10 to the 6 micrometers. One times 10 to the 6 micrometers. The micrometers cancel. So take 50 and then divide by 1 times 10 to the 6. And you get 5 times 10 to the negative 5th meters. And so that's going to be right in the IR region. And so we looked at the visible region of the IR spectrum with its wavelengths ranging between 400 and 700 nanometers. And so what determines the color of light? is going to be the wavelength. And so therefore, if we want to describe the differences between orange light and violet light, orange light is going to have a longer wavelength than violet light, but orange light is going to have a lower frequency than violet light. And so question 5, I completed parts A and B of question 3. You're to complete C and D, converting those units to meters, and then finding what region of the electromagnetic spectrum that light with that wavelength will correspond to. And then in question 5, arrange the wavelengths in terms of increasing frequency. So therefore, the longer the wavelength, the shorter or the lower the frequency. So therefore, for part A, the answer was 1 times 10 to the negative 2 meters. For part B, the answer was 5 times 10 to the negative 5 meters. So therefore, A has a longer wavelength than B. So therefore, A will have a lower frequency than B. And so you would need to complete C and D and then arrange those in order of decreasing wavelength. By arranging them in order of decreasing wavelength, you'll also be arranging them in order of increasing frequency. So arranging in order of decreasing wavelength is the same thing as arranging them in order of increasing frequency. So question 6, calculate the wavelengths of light having the following frequencies. So earlier we said that the speed of light, which is c, the speed of light is going to be equal to the wavelength times the frequency. The speed of light is a constant, 3 times 10 to the 8th meters per second. So therefore, if we want to find the wavelength, we can rearrange this equation and solve for wavelength. So if C is wavelength times frequency, wavelength is C divided by the frequency. So therefore, wavelength is going to be the speed of light, C, divided by the given frequency. The seconds cancel. You do the math, 3 times 10 to the 8th, divided by 6.79 times 10 to the 14th. You'll get 4.42 times 10 to the negative 7. and the units are meters. And so we said that there's an inverse proportional relationship between wavelength and frequency. The higher the wavelength, or the longer the wavelength, the smaller the frequency. However, energy has a directly proportional relationship with frequency. So those same wavelengths in question 3, if you arrange them correctly in order of increasing frequency, then that is also the same as the order of increasing energy. So basically question 5 and 7 will have exactly the same answers. So question 8, you have the frequency of a microwave oven given. And so part A is microwave radiation more or less energetic than radio waves. Well, microwaves have shorter wavelengths than radio waves. So microwaves have higher frequency than radio waves, and therefore higher energy than radio waves. So is microwave radiation more or less energetic than radio waves? More. They are more energetic. And then B, is microwave radiation more or less energetic than X-rays? Well, based on their position on the electromagnetic spectrum, X-rays have shorter wavelengths than microwaves. So X-rays have higher frequencies and higher energies than microwaves. So is microwave radiation more or less energetic than X-rays? Microwave radiation is less energetic than X-rays. And so question 9, UVA, UVB, and UVC radiation. These are different types of ultraviolet radiation. So you can categorize ultraviolet radiation as UVA, UVB, or UVC. So UVA radiation, it makes up about 95% of all the UV rays that make it to the Earth's surface. So UVA penetrates deep into our skin and can even pass through glass. So UVA damages your skin, resulting in a tan. So it's the primary radiation type that's used in tanning beds. So UVA radiation, therefore, going to have the longest wavelength of the three types. UVB radiation also reaches the Earth's surface. UVA rays penetrate more deeply into the skin and play a greater role in premature skin aging changes, including wrinkle formation. And so UVA has the longest wavelength. UVB radiation's wavelength is in the middle. UVC has the shortest wavelength. So arranging them in order of increasing wavelength, UVC is shorter wavelength than UVB, which has a shorter wavelength than UVA. And so therefore, by UVA having the longest wavelength, they have the smallest frequency and therefore the lowest energy. Whereas UVC having the shortest wavelength has the higher frequency and therefore the higher energy. And so therefore, in order of increasing energy, is the opposite. UVA has smaller energy than UVB, which has smaller energy than UVC. And so now the potential, therefore, for biological damage, that means that which one has the greatest ability to damage your DNA and therefore cause skin cancer. It's going to be the highest energy and therefore highest frequency. So UVC will have the highest potential. And UVA will have the smallest potential. And I'm not going to put UVC because UVC, thank God, never makes it to the Earth. So therefore it doesn't have potential. But if it did make it to the Earth, then we wouldn't be here because it would kill us off quickly because it would damage our DNA so badly that we'll have the radiation sickness and therefore we would die. So UVC never reaches the Earth. And the reason why it never reaches the Earth is because we have an ozone layer in our stratosphere that blocks it. So it never reaches our troposphere. It never reaches the surface of the Earth. So it doesn't have a potential to cause biological damage because it never reaches us. But UVB does reach us, and it has a higher energy than UVA, so it has a greater potential for biological damage than UVA. So if the distance between the sun and the earth is 1.50 times 10 to the 8th kilometers, how long in seconds does it take light to travel from the sun to the earth? Well, we know that the speed of light, c, is 3 times 10 to the 8th meters per second. And speed is distance divided by time. And c is the speed of light. So what they're asking us to solve for in this problem is time. Well, we know what the speed of light is. We know what the distance is. So we need to solve for time. So we rearrange this equation and solve for time. So time will be equal to the distance divided by the speed. So therefore, the time it's going to take for light to travel from the sun to the earth is going to be the distance, 1.50 times 10 to the 8th kilometers, divided by the speed, which is 3 times 10 to the 8th. Meters per second. Well, we've got a little problem here. I can't cancel a meter out with a kilometer. So I've got to use a conversion factor. For every 1 kilometer, there are 1,000 meters. So we're going to need to use that conversion factor so that we can cancel out the meters and the kilometers. So kilometers are in the numerator. So in our conversion factor, we need to put kilometers in the denominator. And meters are in the denominator here. So we're going to need meters to be in the numerator of our conversion factor so that the meters cancel. So now we do the math, and our units are the time units that we want, seconds. So 1.50 times 10 to the 8th times 1,000 and then divide by 3 times 10 to the 8th. And we get 5 times 10 to the 2 seconds. And so in looking at the periodic table, we can determine the number of valence electrons that an atom has based on its group number. The number of valence electrons are the outermost energy level orbital electrons. So it's the electrons that lie in the outermost occupied energy level orbital. And so aluminum is in group 3A, so it has 3 valence electrons, whereas lithium is in group 1A, so it has 1 valence electron. Sulfur is in group 6A, so it has 6 valence electrons. Fluorine is in group 7A, so it has 7 valence electrons. Nitrogen is in group 5A, so it has 5. And argon is in group 8A, so it has 8. And so when we draw Lewis dot structures for an atom, we draw the Lewis dot structure for an atom by placing the number of valence electrons that that atom has around the atom in pairs of 2, maximum. And so we start by simply adding 1 electron at a time to each side. Oxygen being in group 6A, it has 6 valence electrons. I symbolize an electron with a lowercase e and a negative sign. So oxygen with 6 valence electrons. Now I've got 4 on either side. So now I'll add the remaining 2 by pairing up. So there's the Lewis structure for oxygen. Chlorine is in group 7A. It has 7 valence electrons. And so again, I write the symbol for the element. I put 1 dot representing 1 electron. Each dot that I'm putting is representing an electron. So there's 4, but I need 7, so I'll start adding additional electrons by pairing the additional electrons up with the one that's already there. So now I've got 2, 4, 6, 7. Calcium is in group 2A, so it only has 2 valence electrons. And so there's your 2 valence electrons. And so in addition to drawing Lewis dot structures for atoms, you can also draw Lewis structures for molecules, ions, or radicals. And so you do so by summing up the number of valence electrons for each atom that makes up the molecule or ion. So for CCl4, you've got carbon, which is in group 4A. So there's 4 valence electrons. And we only have 1 carbon in the formula for the compound. But you've got also chlorine. Each chlorine is in group 7. So there's 7 valence electrons per chlorine, and you've got 4 of them. So adding 28 plus 4, that gives you a total of 32 valence electrons. The least electronegative atom in the Lewis structure is usually the central atom. Carbon is less electronegative than chlorine. So carbon will be in the center, and connected to it in single bonds will be the 4 chlorines. Each of these straight lines represents a single bond. Each single bond represents 2 electrons. So each of these single lines represent 2 electrons, and that's called a single bond. So far I've put in 2, 4, 6, 8 of the required 32 electrons. So I need to put in all 32. And so now I follow what's called the octet rule. My central carbon now has 2, 4, 6, 8 electrons around it. So the carbon is happy. So now I've got to make sure each chlorine has 8 electrons surrounding it. So now I add the additional electrons as dots around the peripheral atoms. Carbon is the central atom. Each chlorine is a peripheral atom. So now I've got 2, 4, 6, 8 electrons around this chlorine. And I'll do the same for the other 3 chlorines. Put the 6 dots in pairs of 2 around each of the other peripheral chlorines. And they'll have the octet rule satisfied for them as well, having 8 total electrons surrounding. And there is your Lewis structure for CCl4. Now the oxygen molecule O2, each oxygen is in group 6, so 6 valence electrons, and you've got 2 of them. So you've got a total of 12 valence electrons. So you connect each oxygen to the other with a single bond. And then you put the pairs of dots around each of the oxygen so that each is now surrounded by 8 electrons total. And then we count up the total electrons we've put in. We've got to have a total of 12, 2, 4, 6, 8, 10, 12, 14. Okay, we've got too many. We only need 12. So whenever you've put in too many electrons, you take away a pair of electrons from each of the atoms, and you replace those electrons you took away with another bond between those atoms. So now you've got a double bond between each oxygen. That double bond represents 4 electrons. Remember, a single bond represents 2 electrons. A double bond, therefore, will be equal to 4 electrons. So now I've got 2, 4, 6, 8, 10, 12. And each oxygen's octet rule is satisfied because each oxygen is surrounded by 2, 4, 6, 8. 2, 4, 6, 8 electrons. Now O3 is ozone. Again, you got 3 oxygens this time. Each one has 6 valence electrons. So ozone has a total of 18 valence electrons. So I put single bonds between each oxygen. Each of the single bonds represents 2 electrons. And then I satisfy the octet rule for each oxygen, placing single electrons in pairs around each oxygen so that each oxygen is surrounded by 8 total electrons, satisfying the octet rule. So then I do my electron count to make sure I've got 18, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Again, just like with oxygen, I put in too many. So I need to erase a pair from the central atom and a pair from one of the peripheral atoms. And then I replace those electrons I erased with another bond between those 2 atoms, giving me a double bond. So now I see I have 2, 4, 6, 8, 10, 12, 14, 16, 18. So now I've got my 18 required total electrons, and there are 8 electrons around each of the oxygens. And so there are several of these left to do. I've done A, B, and C. D, E, F, and G are not molecules like A, B, and C were. These are ions. So when you have a positively charged ion, that means that the central atom has lost 1 electron. Or in part E, F, and G, you have a negatively charged ion. That means that the central atom has gained 1 electron. So therefore, the number of electrons that are lost or gained is equivalent to the magnitude of the charge. So this is a +1 charge. This is a -1 charge, -1 charge, and a -1 charge. So for E, F, and G, the atom has gained 1 electron. But for D, the central nitrogen atom has lost 1 electron because you have a +1 charge. So therefore, to get the total valence electron count for NH4+, the nitrogen is in group 5, so it has 5 valence electrons, and there's just 1 of them in the formula. And then you've got hydrogen. It's in group 1, so it has 1 valence electron, and there are 4 of them in the formula. Add 5 plus 4, you get 9. But then you've got to subtract 1 for the 1 electron lost due to that +1 charge. So 9 minus 1 is 8. So you've got 8 valence electrons. So your nitrogen is the more electronegative atom. It goes in the center. The 4 hydrogens are bonded to it. And you've got 2, 4, 6, 8 electrons, as represented by those 4 single bonds. Each single bond represents 2 electrons. And then it's an ion with a +1 charge. You put the Lewis structure in brackets, and then you put the plus charge on the outside of the brackets. For part E, you've got NO3 minus 1. So again, you've got 1 nitrogen in this formula in group 5, so it's 5 valence electrons. And you've got 3 oxygens, each in group 6. So 6 valence electrons times 3. (18 plus 5 is 23. Then you've got to add 1 electron for that -1 charge. So there's a total count of 24 valence electrons. So your central nitrogen is going to be connected to the 3 oxygens via single bonds. And then you'll place your single paired electrons around each peripheral oxygen atom, giving them a total of 8 electrons surrounding them. You can see the nitrogen only has 2, 4, 6. It also needs 8, so we'll put a lone pair of electrons over the nitrogen. So now we do our electron count: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We have too many. We only need 24, but we put in 26. So we're going to erase 2 electrons from our central and 2 from one of the oxygens. It doesn't matter which one. And then we're going to replace those electrons that we erased with another single bond, giving us a double bond between the central nitrogen and that oxygen. Now we've got our 24 valence electrons, and we've got our ions Lewis structure completed. We'll put it in brackets and put the minus sign outside of the brackets. And so question 14 is about chlorofluorocarbons. Those were compounds that were once used in hairsprays and refrigerators and air conditioning, but they're not used anymore because they react very vigorously in our stratosphere with the ozone, and therefore they break down ozone, which is a bad thing because we need our ozone layer to protect us from things like that harmful high energy, high frequency UVC radiation. But CFCs were very desirable for use because they were cheap, easy to manufacture, very cheap to manufacture, and they had the properties that we wanted them to have of being able to be compressed easily and put into aerosol cans and to be used for like hairspray purposes. And they were also very, very good refrigerants. So therefore their uses in refrigerators and air conditionings were very desirable. But that made them desirable, but their undesirable quality, of course, is that they destroy ozone. So that's why we don't use them anymore. We replace the chlorofluorocarbons because the chlorine part of the chlorofluorocarbon is what reacted with the ozone. So therefore, they've replaced chlorofluorocarbons with by replacing the chlorine component with another atom like additional fluorines or additional carbons instead of having those chlorine atoms as a part of the compound. So we have some modified compounds that we use now as refrigerants instead of the CFCs. And so the free radical that plays a role in catalyzing ozone destruction is going to be this one, the ClO minus. Ion. And this ClO is ClO. It's not a minus sign, actually. It has a little dot there. And that little dot that's an unpaired electron. Remember, a little dot in a Lewis dot structure represents an electron. So here, the ClO species with that one dot on the oxygen, that means that's an unpaired electron. And electrons don't like to be unpaired. Electrons like to exist in pairs. So therefore, this is called a radical because it has an unpaired electron. And radicals are very reactive because of the unpaired electron, because that electron is going to want to hook up with another electron. And that's what makes it so reactive. And so therefore, when this compound gets produced from the breakdown of a chlorofluorocarbon, that ClO radical is going to react so fast with the ozone and break that ozone down. So that's what makes this species so reactive, is because it's a radical, meaning it has an unpaired electron that is very unhappy being unpaired. So it's going to want to react with a substance like ozone so that it can pull an electron off of the ozone. And that brings us to the end of the Chapter 3 practice problems.